And for the third time already?
Maybe, yes.
Yes,
Thank you very much for this invitation and for coming. Maybe let me shrink it a bit. Okay, as mentioned, I will talk about this maximum entropy random walk, which is the random walk chosen according to the maximal entropy principle. Yeah, so this principle is crucial for statistical physics model. That if we don't know something, some parameters, the safest assumption is are the maximizing entropy one. Yeah, so there are many reasons to use this principle, also to choose diffusion random walk. And if you do so, the disagreement between quantum predictions and diffusion world predictions no longer disagree. Yeah, so now we have diffusion people, quantum mechanics people, and for example, for 0-1 range, diffusion people would say that stationary probability distribution would be uniform, the one here. But quantum mechanics people, we say that it should be sine square. So this is the same situation, the same question, what is the stationary probability in 0-1 range? And these two societies work with different answers. So the question, let us try to understand it and repair it here. So like here, so we have these two basic possibilities to choose random walk on a graph. So we have a graph, and natural way is that you have a walker if this drunken sailor sees three possibilities, just throw a dice and choose one. Let's say we've chosen probability as maximizing entropy in given step. However, if we calculate mean entropy production, this is not the best. The best would be uniform distribution among paths, not steps, but paths. Yeah, so that's the crucial difference if we think about locally maximizing entropy for given steps, each step separately, or average. If you do average, we get slightly different the stochastic matrix, stationary probability distributions. So, for example, here is the example for the semiconductor that we have a lattice with defects. Defects means that there was a removed self loop in this lattice. And we take a look what is the stationary probability distribution after 10 steps, 100 steps, 1000 steps. So we can see that after 10 steps, they look similar for standard random walk and this maximal entropy random walk. After 100, there are some differences, but for 1000 it's completely different. Yes, the standard random walk leads to nearly uniform distribution, while the maximal entropy random walk and quantum mechanics, the formula will be the same, leads to this localization. It's called Anderson localization. So for semiconductor, it is crucial that if we have this distribution of electrons, if we attach potential, electric potential, electron would flow. So this is a conductor, while we know that semiconductors are not conductors. And here we can see that it's not a conductor because the electrons are imprisoned in this Anderson localization. If you attach potential, it's much more difficult to make them flow. Yeah, so if you want, there is this Wolfram. I put it in the chat previously, easy find. There is this animation that we have. Maybe let me turn on the Mathematica version. So we have now defects as remove some edges on our graph. Standard random walk, stationary distribution look like that. That there is nearly uniform distribution, and they're only slightly reduced near the removed edges. But for maximal entropy random walk, the distribution is completely different. Yeah, so we can see that this Anderson localization, this is no longer a conductor because now we can attach the potential. So we can see that it's for higher potential it starts being a conductor, but for small one there are problems. It's more difficult to make the electrons flow here. You can make the electrons flow. So we can see that this very sounds subtle difference, but it's crucial difference. It's completely different if you use standard random walk, maximizing entropy locally, and maximal entropy random walk, maximizing entropy globally. So it's completely different. The second is in agreement quantum mechanics. The first one is completely in disagreement, and people from diffusion only work on this one and get completely different predictions than quantum mechanics people. We can understand by this entropy maximization here. Okay, so I will show it from various perspectives. It has many different applications. So the original one is the information theoretic applications like optimal coding for given constraints. Then the quantum part, the most important for this audience, maybe also some different applications depending on the time. Okay, so the last time I have talked about a lot of about these droplets. Yeah, so they have this shaker, and then there is this droplet couplet with wave it creates, getting many quantum effects like the double slit experiment with interference, the oblique quantization, but also these statistics. If they look at statistics, they get quantum-like statistics. Yeah, so this is what we are interested in. Yeah, so understanding why they don't get these standard diffusion statistics, but quantum mechanical statistics. Yeah, so that's very. So if we use maximal entropy random walk, we can understand it. We will derive it. Yeah, so we have some droplets with very complex behavior because there are these couplet waves. So this is very difficult to analyze, but we would like to use statistical physics approach that we don't know the details, but would like to find the most likely statistics. Yeah, so the statistical physics approach. So for this purpose, we need to use maximal entropy principle. Otherwise, we get completely different predictions, like standard diffusion people do, in disagreement with this kind of experiments in quantum mechanics. Okay, so here is some overview of the slides. So here is this 0-1 range I have mentioned. So standard people would say there is uniform distribution for 0-1. Then we would get it by using uniform ensemble among paths. Yeah, so we get this Boltzmann distribution in space, which is uniform here. Then we could use ensemble of half paths from now toward future or from now toward past. And if you use that such ensemble of half paths, uniform ensemble, then we find further that we can get the first power of quantum amplitude. But if you use ensemble of full paths, then literally we have to multiply the two amplitudes. Yes, to get a given position, we need to get it here and here. So we need to multiply the two amplitudes. So we get the Bohr rule exactly from symmetry of time. Yeah, so I think this is very important. That people say that Bohr rule is some magical entity, but if we just do think about ensemble of paths, also in Isaac model, we have ensemble of full paths. If you use ensemble of half paths from now toward left or right or past or future, you get first power amplitude. But if you use full paths, we need to multiply the two amplitudes, getting the squares, getting the Bohr rule. Yeah, okay, so we have these three philosophies. So the standard philosophy, the diffusion people use in disagreement quantum mechanics and maximizing principle is that they guess some stochastic propagator. Yes, if you look at what they do, like this the Drunken Sailor, one third, one third, one third. We don't know, so let's assume that the simplest model. So this is simple, but just arbitrary. Yes, we guess literally. They guess. So from the other side, we have ergodic picture that we assume some deterministic trajectory and average this trajectory. But again, do we know that exact formulas for this deterministic trajectory? Usually we don't have. So this is again simplification. So now this is the most, I think, the safest approach, the statistical physics approach. That if we don't know what's happening, if you are in a given position, we should assume ensemble of paths from this position, and from this ensemble find the stochastic propagator. What is the probability of being the next position? Yeah, so we don't no longer guess the stochastic propagator. We find it from the maximal entropy principle from ensemble of paths. Yeah, and this finally agrees with quantum predictions. Like for these droplets, they also get these paths, and they average to quantum statistics, not stochastic people. Also for neutrons, they also get, so this is classical. The black line is the classical for neutron, but they get the excited statistics. Again, the question is for which objects we should get classical statistics and for which quantum. This is a very difficult question, but if there is, like for these droplets, there is some couplet wave with very complicated behavior, it's much better to use this statistical physics picture instead of guessing some stochastic propagator, which is completely usually incorrect. Okay, so let's go to this entropy maximization. Yeah, so I usually teach from this simple situation that imagine we have a sequence of zeros and ones of cell length n, and we know the probability of ones, the black dots. Yeah, so what is the number? So the number is this binomial. but we would like to have the asymptotic behavior from n to going to infinity. And if we do it with string formula, we can easily get this formula that asymptotically it is close to this 2 to power n times Shannon entropy. Yeah, so here is the Shannon entropy. Yes, so now we can think about this James principle of maximal entropy, that if we don't know what is this P, what P should we choose? Yeah, so we can see that this P is in its exponent. Yeah, so if we choose the h of P which maximizes entropy, this 1/2, which is 1 bit, yes, if we choose here, then this subset of possibilities will grow with the highest exponent. So asymptotically, it will dominate all the possibilities. Yeah, so choosing P equals 1/2, we choose a subset which will grow the fastest. Yeah, so asymptotically, all the rest should be non-important. So this entropy maximization is just working on some ensemble of possibilities and focusing on the fastest growing subset. Yes, so this principle of we don't know something, so we just choose the safest assumption, describing the subset which grows the fastest, which will dominate asymptotically all the rest. Okay, so yeah, so I hope I have convinced you that if you don't know some parameters and there are no reasons to assume otherwise, there is no bias there, we should choose parameters which maximize entropy because they correspond to the highest exponent, so this subset will grow the fastest. Okay, so let's think about this conflict between entropy growth and this CPT symmetry. Yeah, so very briefly, from one side, it is believed that equations governing physics are symmetric. This is crucial. That CPT symmetry is crucial for modern physics. However, clearly entropy is not it's not symmetric. Yeah, so we believe that entropy grows. So, how to get this entropy growth if the equations are symmetric? So first of all, I show this simple situation that if you have a lake surface, it is symmetric in equations, but if you throw a rock in solution, it is not symmetric. Yeah, so still in equations there is symmetry, but in the solution we can see so it is very common to break symmetries, the fundamental symmetries in the solution. And for example, the Big Bang was, I think, the reasons why the main reason for the second law of thermodynamics, everything was localized, so entropy was low, creating this entropy gradient. We know we named the second law of thermodynamics. So generally for classical evolution, there is no entropy. We know everything. So assuming that we know the equations and the positions, then entropy is zero. However, there are these theorems like this H theorem, Boltzmann H theorem, which proves entropy growth. But there is always some infinite approximation hidden. So always, I show it, for example, here that if you think about this tank with molecules, if you think about classical trajectories, there is zero entropy. You know all the positions of the particles, but now you can approximate it with some one parameter p. What is the percentage of particles being in the left part? Yes, you can do it, and if doing so, you can easily get that entropy should grow to p equal 1/2 here, and so the density should be equal. However, this assumption, this p, means that you smeared the particles over the entire part. Yeah, so this is mean-field approximation. Going to this p is mean-field approximation. If you would first apply the symmetry, then use this approximation, then you'd get entropy growth toward the opposite direction. Yeah, so you should be very careful about this entropy growth. So very briefly, I showed this slide I do today, but generally, if you think about about Big Bang and assuming that there will be a big crunch, if you think about a thermodynamic situation, it should be very similar. The entropy should be very similar here and here. So the big question is why it drops. So finally, if you think about this scenario, we can see that entropy doesn't have to always grow. So finally, it would have to decrease. Yeah, so from symmetry, but maybe let me skip it. Okay, so let's go to MERW. That's the simplest situation, maximal entropy random walk. Yeah, so this simplest graph. Yeah, so we have these just two positions, and we would like from one, we assume that we have to go to zero, but from zero we can go to zero or to one. Yeah, so the graph is given like here. The question is what Q should we choose? Yeah, so naively we would choose 1/2. Yeah, so but I will try to convince you that 1/2 is not the best choice from entropy maximization perspective. And to make it more concrete, there is this Fibonacci coding scenario that we have these sequences of zeros and ones, but after one you forbid two neighboring ones. So after one you cannot use another one. Yeah, so this restrict the space of sequences, and this way you can encode a smaller number of bits per symbol. And now you'd like to find the what number of bits per symbol you can hide here because of the constraint, and how to do it, how to encode inside with such constraints. So so we can use this stochastic matrix that after one we have to use zero, yes, because of the constraint, but after zero we use another zero probability q, or one with probability one is q. And the question is, what q should we choose? If you choose, so here is the, so after choosing some q, we can find the stationary probability distribution, the rho, which is this eigenvector for eigenvalue 1, so which is easy to find here. And you can find entropy, but this is, so this is not just, so you can recognize here is entropy, Shannon entropy. However, there is also question, what's the probability of using each position? Yeah, so we need to average this entropy times the probability of being given vector. Yeah, so this is called entropy rate, just mean entropy. Yeah, so performing this Markov process, random walk, what is the mean entropy per step you produce? And if you calculate it, you get this plot. We can see that 1/2, this naive choice, is not the maximum. The maximum is here, which is q for q equals 0.618, the golden ratio. Yes, so let's try to understand why the 1/2 q is not the optimum here. Yes, that because if we increase the q, then we will reduce the number of of entropy in this step. However, we increase the probability of being in the zero state. Only from zero we can produce entropy. Yeah, so we try to go to one less frequently to be able to more frequently to produce bits. Yeah, so it's this way. It's better to try to shift this q from 1/2 toward one, because um, this way we will be more frequently in zero, and finally we get more bits per symbol. Yes, and we could find this q. So I will show some derivation how to get this q here and generally. But the simplest way, if you think about this sequence of this Fibonacci sequence without two neighboring ones, to find the q, you would have to think not about the steps, but about entire sequences. Yeah, so we need to think about the space of sequences, and we have to say that each sequence has the same probability. And now from this ensemble of sequences, look what is the probability that after zero is zero. And here we get the q, not from the ensemble of steps where you get this unoptimal standard random walk, but from an ensemble of paths, entire paths, infinite in practice. Okay, so here is the original motivation. I work on this in my third master thesis, 2006. So my original motivation was to encode the information inside this two-dimensional version of Fibonacci coding. But again, you cannot have two neighboring ones, but now in 2 dimensions. So this is much more difficult situation. So it turns out, so for 1 dimension, this constraint reduce the number of bits per position from 1 to 0.69. Here for 2D, it's called hard square constant 0.58789. So it is not like 80 bits, 80 digits. So in Baxter book, so it is not analytically found, but we know very closely what is this capacity. So how to calculate this capacity? So to find it, we need to think about some areas here and calculate what is the number of possibilities in this area. Take a logarithm, divide by area of this region, and take the limit to infinity. This way, in this limit, we will get this number of bits per position. We can, on average, write. But the question is how to encode information close to this theoretical limit. Yes. So and why? So let's think about the application. So the application is, if you think about hard disk, that they have these magnetic dots, and you just put one or zero in given position. And now we would like to squeeze the lattice. If you squeeze it by square root of 2, now the dots will touch each other on the diagonal. So this way, but you cannot now use two neighboring ones. If you magnetize this dot, you shouldn't do it for this this dot. And so you get exactly the constraint we are talking about. Yes, so from one side, from this squeezing of lattice, you increase the number of positions by the square root of 2 squared, so by 2. From the other, the constraint has led to the 0.587 bits per position. So finally, if you multiply them, you get 17.6% improvement. Yes, so now you can encode 70% more. And if you would use larger and larger, you could increase it to a few maybe. So you get 70% improvement by better positioning, you can say, of the head. So now I would say how to encode it. So how I did it. So I took a finite width like 20 lattice and took such slices. Yeah, so we got one slice and the next slice, and found them allow slices by the constraints, and found what slice could be next to the previous slice. And using this maximal entropy random walk, I can find I can get the stochastic matrix. So what is the probability of the next slice? And then I can get to such scanning algorithm and get the optimal probabilities. And then I have introduced ANS in 2006, which is now quite popular originally to encode in this lattice with this stochastic process. I can approximate. Yeah, so we can like here we can find the probability here was just Q, and you can use entropy coder for that to encode with this Q, and here this Q can vary with the position. Okay, so to summarize, so we have some graph which says what transitions are allowed, and now you'd like to find the stochastic matrix. So just assign the probabilities which sum to 1 for all outgoing, such that this mean entropy production, so not just entropy but average over the stationary probability distribution, is maximized. So for standard random walk it's not, but as for this Fibonacci, we should find ensemble of paths, not just single steps, but paths. So ensemble of single steps maximizes entropy locally, but not globally. For globally, you need to use ensemble of entire paths, infinite, for example. Or there is also final definition that for each two positions and length, every path of given length has the same probability. Yes, this and this has the same probability. So now you can see them. As I have said, shown on the first slide, and here is the experiment. So what is the stationary probability distribution of electrons in semiconductor? So you can see it's much closer to this maximal entropy random walk, which is also the same as quantum mechanics, completely different than what stochastic people, diffusion people do. So they use some approximation, they guess stochastic propagators, but it's incorrect. It's approximation. We can repair it by this entropy maximization to get closer to experiments and to quantum mechanics. So toward ensemble of paths, not of steps. So from philosophy perspective, in standard random walk, we assume that we know the use probability distribution used by the Drunkens-Taylor. And it has characteristic step that the Drunkens-Taylor sees one steps and use the probability among these possibilities. For MERW, it's completely different. For MERW, we don't assume that this walker uses our stochastic matrix. Instead, the walker just performs some complicated behavior, like for these droplets with couplet waves, and only we use this maximal entropy random walk to find the most probable probability distribution of walker, where to find it. And it no longer has this characteristic length. It's kind of scale-free limit of the standard random walk, because we take the paths and you use the infinite paths finally. Okay, so this is this infinite path. So we have this very simple graph, just four vertices. And the question is, what is the probability distribution for jumps from this position? So from standard random walk, we say 1/2, 1/2. So we have one path up, one path down. Now you can think about paths of length 2. So for up we have 1, so here and here. For down we have here and here. We have 2 paths of length 2. Length 3, length 4, and so on. So for each of them, you can use the probability. So here you have the probability 1/3 going up, 2/3 going down. here two-fifth, and so on, and we take the infinite limit. Yeah, so we imagine that the walker thinks about infinite paths toward future, and from them you finds this probability distribution for one step. Yeah, so if you do it, we get this maximal entropy random walk. So so here is 0 to 382 for going up asymptotically. So I maybe derive later. So here is article which finds the entropy for various real networks using this GRW, this basic of length 2 paths, length 3 paths, and MERV as infinite limit of this GRW, and we can see that entropy quickly goes to the maximal one being 1 here. However, the stationary probability distribution usually is far from the maximal entropy random one. Okay, we have also some different scaling variants. So here was scaling variance in time that that GRW chooses them this one step, only this Duncan Sailors is one position, while MERV kind of sees to infinity. Yes, it does no longer sees the step size. And we can also think about this kind of property that you have the stochastic propagator and perform L steps with that. So from MERV, it is the same as just taking the matrix and performing M to L and making this the MERV, but for standard random walk, it's not. It's completely different. Also, we can get it's more time symmetric. So MERV is time symmetric. GRW is not time symmetric. So I'm also showing later. Okay, so let's think about simple derivation. Yeah, so let's derive the formula on example of this again. This graph of four vertices. So here is this graph and time in the vertical direction. So here we have the paths, and we would like to assume uniform ensemble among paths, and ask what is the probability distribution of each vertex among this ensemble of paths. Yes. So from combinatorics we can find the formula. We have this m to power t is the of position yx is the number of length t paths starting in y and ending in x. Yeah, so for paths starting from here and going to here, this power calculates the number of paths from here to y, and we can sum over y, possibly y, and the same we have to do for up. So this way you get this formula, and now we like to make them the limit t to infinity, this length of paths to infinity. And there is this so-called Frobenius-Perron theorem saying that for nice graphs like connected aperiodic, usually this M has one dominant eigenvector, eigenvalue, so we can use just the dominant eigenvector, eigenvalue. Yeah, so and we can see that we got the Born rule as mentioned. Yeah, so literally one psi goes from these paths from the future, and one psi from paths from the past. Yeah, so literally, Born rule comes from symmetry. Also from Isaac model. So also in this S matrix, we have this kind of formula that we have one amplitude, second amplitude, and there's some unitary matrix between them. And again, these amplitudes we should evolve, but they come from propagating from minus infinity to now and from plus infinity to now. Yeah, so literally like here. Yes, exactly. Born rule comes from time symmetry. We can also find the stochastic matrix this way. Okay, so here is this neutron. So here is the classical for neutron, but they got the dots which correspond to quantum. So also neutrons behave like this according to maximal entropy random walk or quantum mechanics, as you call it, because the formula are the same. So standard random walk is wrong. Just yes, standard diffusion says this, but they see this. And again, this Born rule comes from if you use ensemble of paths from now toward future, you get first power of amplitude, or also from the second direction. But if you use ensemble of 4 paths and you like to get some point randomly, you need to get it twice, so you need to multiply 2 amplitudes. You get the Born rule from symmetry. Yeah, so and having this Born rule from symmetry, you can get variation of Bell-like inequalities. So I usually show this MERV inequality, which is very much simpler than Bell's, because so if people say that they can validate Bell, I ask them about MERMs, and it's and they give up, so that they stop responding. So I think this is very good. If somebody shows you that he has Bell validation, ask him about the MERMs. So it is just tossing three coins at least to give the same. Yeah, so completely obvious. And so you can write it around this probability that so we have ABC coins, 0, 1 variables, and the sum of probabilities should be at least 1. So let's so it's obvious, but quantum mechanics allows to validate it. So let's show a simple proof. So this case A equals B corresponds to these 4 possibilities among 8 possibilities for 3 binary variables. Yeah, so these 4 ones. Then we add the 4 ones for this equality and for this equality, and we get like something like that. Yeah, so we have at least 1 everywhere. So whatever joint distribution you choose, it has to be at least 1. Yeah, so we have just proven this inequality. Yes. However, we have used this Kolmogorov third axiom that probability of alternative is sum of probabilities. Yes. Instead, in quantum mechanics, you can replace it with this Born rule. So that's the real problem, that we prove some inequality based on one rule, and now we replace this rule with a different one, so this inequality does not longer have to hold. So if we have the Born rule, like mentioned here, then, for example, for Ising model, we can also get this validation. So let's choose this amplitude with zeros in the place of these three, so they are on the most important positions, but let's put it here for amplitudes. And now we can get the validation to 0, 0, 6, below 1. For example, with Ising model also, because it also uses ensemble of paths. So imagine we have Ising of model of sequence of 3 spins. So 3 spins up, down, but with constraints which forbid them which make the 2 zeros here. So you forbid 3 up and 3 down. So if you do it, then for probability at the end of sequence, you would get this amplitude. So if you just think about the end of sequence of Ising sequence, you get this probability distribution. But in the center, again, you have to multiply 2 amplitudes. You get the squares. Yeah, so you get the validation of Bell-like inequalities in the Ising model. Yes. Okay, so here I have some plot, but maybe let me skip it. Okay, so here is some summary of the 2 random walks. So here we have some graph given by this adjacency matrix M. For standard random walk, you would say that the probability is just uniform among what the Drunken-Sailors is. But for MERW, it's more complicated. You have to find the dominant eigenvector of this M matrix, and this is the formula for stochastic matrix. For a stationary distribution, so you have the Born rule. However, so this is for symmetric, if the M is symmetric, but if it's not symmetric, you have to calculate the left and right dominant eigenvector and multiply them. So it's quite kind of similar for this like in S matrix. While for standard random walk, we just this probability is proportional to the degree of vertex. So we can also easily reverse time. So to reverse time so here is reverse time. So we have to just use the second derivative and just multiply in the opposite direction, and you get reverse time. Also here is the probability of paths. So for MERW, this is usually this is 1. So all paths of given length between 2 vertices have the same probability. While for standard random walk, this is no longer symmetric because you have the first position but not the last. You miss so it's not time symmetric. Also, the entropy formula is much simpler for MERW, but here you have some complicated formula. So generally, that's a big question. So diffusion people only use standard random walk, but maybe we should think about going here, because for many cases it might be safer choice. The big question is when MERW is better, but that's a very difficult question. The definitive for electron, for neutron, you should use MERW, but the question is about larger objects. So the question is when should you use standard random walk? So that, yeah, so I think this is very, very difficult. Okay, so maybe let's go to some different situation. For example, for Isaac model. So there is we can use it for Isaac model, also for Boltzmann distribution. So here, for example, there is for Isaac model, they are so-called Markov fields. So Markov fields is something like that having the probability, having the values of the blue dots to find the probability of this question mark. In fact, we only need the positions of the boundary. So we also need these green dots values. Or also here is some local, here is some more global, that we need only these dots, the positions. And here we can do the scanning. We can scan line by line and find the probability distribution of this question mark based on the blue, but using only the green ones, this boundary. So this is a generalization of Markov property to two-dimensional lattices. And using MERW, you can find this. The scanning approach is the most practical. Yeah. So the question is how to find this probability of given value having the green dots values. So we can do it with MERW. So as mentioned for this hard square to the Fibonacci, we can take some slices. We can slices of width W in practice like 10, 20 maybe, and take all the possibilities for given slice and find them energy or possibility for two neighboring slices, and then from MERW, using these formulas, you get the probability distribution of this 2 by W rectangle. And now you have to marginalize some of the values in the stars, and you get this probability distribution inside your shape. And then you can get the scanning probabilities that having given values in the green dots, you get the probability distribution to use in this question mark position. And it is very nice to approximate, for example, Isaac model. Okay, so now let's go back to Schrödinger equation, quantum mechanics. So let's take a look that we can get the Schrödinger equation, discrete Schrödinger equation for very simple situation with MERW. For as graph, let's choose like this. So we have just lattice with self loops, but some of the self loops are removed as defects. Yeah, so here we have such lattice of length 1000, and here are the defects. The line are the defects. So remove self loop, and there is slightly boundary condition. And here is this for standard random walk, the stationary probability distribution would be proportional to the degree, and degree is 2 or 3, so it's nearly uniform. For standard random walk, it's nearly uniform. But for MERW, the stationary distribution, you can see that here, mostly here, and here is tiny, like a million times smaller. Yeah, so we have this very strong localization, this Anderson-like localization. So they are completely different. Yeah, so this naive random walk and maximal entropy chosen according to the James maximal entropy principle have completely different statistics here. The stationary distribution is completely different. And so here is, you can see that it localizes in the largest defect-free zone. Yes, here or here. And here is very nice that there was just change of one position of defect by one, and now the stationary distribution has shifted from here to here. It's completely different because the two eigenvectors have changed order. The first and second eigenvectors have changed order. Okay, so now we can go to the Boltzmann analogy. So here we have uniform distribution. In this the simplest case, we can also go to Boltzmann, that we add the potential and say that is costly. And finally, we want to get the infinitesimal limit. So maybe let's do it. So now we say that the probability of given path as MERW is here, but now it's not uniform, but it's proportional to minus beta times sum of energies potential on the go. So we get Boltzmann ensemble of paths with energy of path being sum of potential over this path. And if we do it, take the lattice, take some step in time, set the step in of lattice, and we use the MERW formulas. And finally, with approximation infinitesimal limit, we get the stationary Schrödinger equation. Yes, I haven't mentioned that here we get the Schrödinger equation, but the discrete Schrödinger equation. Yes, so the MERW formula was just m psi equals lambda psi, this dominant eigenvector. So, so we can see that here is this m psi equals lambda psi, and m is the previous position plus next position plus the same if the self loop is there. So it's not the defect. If we subtract the 3 psi and multiply by -1, so now instead of maximization of lambda, we get minimization of energy being t minus lambda, and we get this stationary discrete Schrödinger equation to find the amplitude, and then square of this amplitude is the stationary probability distribution. Literally quantum mechanics, but done on paths. In discrete case, we can fully understand everything. Okay, so now we can get, for infinitesimal limit, we can get the rich Schrödinger equation. Just we need to find choose the proper parameters. So what about excited states? So turns out there is something like that. So let's look at this evolution I have shown previously. That after 10 steps you are here, 100 steps you are here, but after 1000 you have slightly shifted. So what's happened? So after 100 it remains not the ground state, but the first excited state. But then it goes to the ground state. Yeah. So first we get subdiffusion to local low energy state, but then we have tunneling to this global state. So there are still excited state, but they are not stable. They want to de-excite to the ground state. Yeah, so it's slightly different. So now excited atom is not. So in quantum mechanics, excited atom without environment would be infinitely excited. But here not. Here excited atom always would like to go down to the ground state. So it's, I think, more physical. So again, these three philosophies, yeah. So this is the standard used by diffusion people, just guessing, propagator, the stochastic propagator, the ergodic philosophy that they assume that they know classical trajectory. Again, it is approximation. In practice, we usually don't know all the details. So this is the safest approximation. This is thermodynamical statistical physics approach that if you don't know the path, we should use a uniform or Boltzmann ensemble of paths to find the stochastic propagator. Yeah, so this is finally chosen according to the maximal entropy principle, and finally in again quantum predictions. Yeah, so these two are approximations. This is the proper way to do physics, and now we don't no longer are the quantum predictions. Okay, so I have more serious article about this semiconductor. I got working diode as p-n junction. That we have two types of dopants. This repulsive, this p-n dopants, and here is the stationary distribution for without potential, and after potential in one direction, potential in the second direction. Yeah, so here you can see that potential in one direction did not lead to conductance, but in the second direction it led to the conductance. Yeah, so we get the proper diode. So here is this current versus the voltage, and you can see that we get in one direction you get the conductance, in the second you get this diode, until you cross some potential, which is called breakdown voltage, when you destroy your diode and you get the flow in the opposite direction. Yeah, so using this properly made diffusion, we can model electronics. Yeah, so the question is, could it be faster than the standard methods? Maybe, yeah, but it needs some collaboration to test it. So for this diode, I need to slightly extend the method, because we don't longer work on single electron, but now on clouds of many electrons, and these electrons inside the clouds are repelling each other. So it's more complicated situation. So for this purpose, we needed to extend this MERW philosophy, that we think about this probability distribution both as the probability distribution of this single Walker, but also as the probability density of the remaining electrons, which are repulsive by Coulomb. Yeah, so you having this probability distribution, we can use the Poisson equation to find the potential this cloud generates, and to modify the potential, and we need to find this and modify the potential, find the density, and do it until we get the same. And here are some examples for this self interaction of these electrons. So here is very here is very strong self-interaction. So if these electrons are stronger, the repulsive, then they destroy this localization. So here is we found this term, this gamma is 0. So this is as previously, just this Anderson localization for single Walker, single electron. But now we increase this self-interaction, and you can see that the electron, the repulsion leads to the density, nearly uniform the density. Here is for repelling, here is for attracting. So it's more difficult, but we can do it. So maybe we could make simulations of electrons this way, but it's very difficult to make software for that. Okay, here is another direction, more recent from the previous year I have done. So there is a big philosophical maybe question. If you use Feynman ensembles, should they be ensembles of physical scenarios, or maybe like this infinite these diffusion-like paths which have infinite velocity, which are nowhere differentiable? So should we use ensemble of these kind of paths, or maybe of smooth paths? Yeah. So in the Feynman ensembles, should we use physical objects, or can we use like this diffusion people now do? So in theory, we can go to these nicer paths, these smooth paths, like in Langevin. So getting kind of combination of Langevin and Schrödinger equation. So getting uniform Boltzmann ensemble among paths, both the diffusion-like paths, but also these smooth paths. Okay, so this is again this 0-1 range. Yes, so this basic case we like to understand well. So the standard ensemble of steps gives this uniform distribution. Ensemble of these diffusion-like paths, which are nowhere differentiable, which have infinite velocity. They are not physical. These two sine squared stationary distribution. But you can use this ensemble of smooth paths, but it leads to different stationary distribution. So that's the big question, which one is right. So how to do it? So again, we get the Schrödinger equation, but now we need to do it like Langevin in phase space. So not only position x, but also position and velocity. So now the basic step is that the position changes by the velocity, and the proper diffusion is in the velocity, like in Langevin. Yeah. So but from Langevin we make this Schrödinger equation. Which is derived in article seriously. So here we have this. So here the Laplacian is not on the positions but on the velocity. Yes, because now diffusion is of the velocity, and here is the coupling between velocity and positions, and here is the energy, kinetic energy. Yes, so now we include the kinetic energy. So now indeed the particle has velocity. Here the velocity, this Laplacian is not kinetic energy. He's just comes from the diffusion. So this is not kinetic energy. Here we need add kinetic energy, and you can see that the stationary distribution is slightly different. Yeah, so you can see that if you use the ensemble of smooth paths, it is easier for the walker to get close to the boundary, the barrier. Why is it so? Because it can get a random, it remembers on velocity. It can randomly gain velocity to make it easier to get close to the barrier. Yeah, so here it doesn't remember the velocity. Here it remembers velocity. It can randomly gain velocity to get close to the barrier. So it's very different behavior. And the big question is, could it be important, for example, for chemistry? Maybe in molecular dynamics, it is worth to include this kind of Langevin-Schrödinger equation to allow the molecules to remember the velocity, to randomly gain the velocity, what changes, especially the tunneling behavior I mentioned in a moment. Okay, so this equation also was found earlier by Bouchard, 2017. I was not the first. So now we have stationary distribution not only in velocity, in position, but in phase space. So here we have the position, and in the vertical we have the velocity, which is the velocity is approximately Gaussian, but not exactly. So we can find it numerically. So here is for harmonic potential. So for harmonic potential, the three possibilities give me the same Gaussian, nearly Gaussian distribution, slightly different Gaussian. The biggest difference is for the this infinite barriers. at the end of this infinite potential well. So you can see that it's easier for smooth path ensembles to get close to the barrier because it can randomly it can gain velocity, what allows it to speed up randomly to get close to the barrier. And for this 1 over Coulomb potential, there is also the small difference. Yeah, so here is standard random walk, and here are the two. So there is some small difference also. So here is a tunneling slide. So for tunneling, okay, maybe let me zoom it. So here is for tunneling. So there is a barrier, and for standard random walk, you can see that there is a diffusion, kind of diffusion through barrier. Yeah, so it diffuses and just randomly goes to the barrier. For MERV, it's different. It randomly gains the velocity and then it pierces the barrier. Yeah, so it's not just diffusion through barrier, but it's literally piercing the barrier. Yes, because of randomly gaining velocity. So there are some small differences. I also was able to get the tunneling right, the behavior, not only behavior from the exponential drop of probability if we increase the width of the barrier, but also the velocity also changes the probability distribution and time of the tunneling. So we can get the proper tunneling behavior here, and very similar they get for this bouncing droplet. There is also this famous article about tunneling for them, and they get exponential behavior with the width of the barrier, and I think also with the velocity there was some discussion. Maybe, I don't remember. Okay, so let me summarize this part. So what I have shown it's very similar to so-called Euclidean path integrals that they do quantum mechanics from ensembles, but in this derotated. So, but there are a few subtle differences. So one difference is that if you look at their equation, it misses the division of these amplitudes. If you want the stochastic propagator, it's crucial. So don't have stochastic. It's something slightly different. So if you want stochastic, you need to use this division. Then use path ensembles on some segments of time, while in MERV use infinite paths, ensembles of infinite paths from minus infinity to plus infinity. Then they start with integration, which is very difficult. So maybe it's better to start with discrete case, which is better for understanding. But the most importantly, they assume quantum axioms and then make this big rotation to imaginary time. So they do some magic. While from MERV perspective, we just do diffusion right, according to this maximal entropy principle. Yeah, so we don't need any assumptions, any magic. We just do diffusion right, and we get the same stationary distributions. Okay, so very briefly, maybe some different. So there is also time dependence that if the potential changes in time, so it's more complicated. That we literally need to have this propagator from minus infinity and from plus infinity, and they have to meet in a given moment. So very similar, like this scattering matrix, for example. And this, I think, it's a nice example that if you have this potential, but we turn it on. So here is potential at the beginning, and then we turn on the potential one. So if we look at propagator from minus infinity, it doesn't see the turning on here, but starts seeing it after we turn it on. If we use from plus infinity, then it starts seeing it before the turning on. And now the final is product of both. So it kind of sees both before and after. Yeah, so but we have to remember that this is only our effective model to best represent our information. So the particle doesn't use, the particle does just have some complicated behavior, and we just would like to find the most probable stationary distribution, for example. Okay, so we get also this continuity equation. Let me skip it. Now, there's another, I think, very nice example. We can get this NFS equation. However, it gets opposite the sign. So this looks funny. But I've talked to people from diffusion, and they also made something similar. But we can understand it why the NFS equation gets opposite sign. So let's think about that. We start with potential like this. That we have minimum potential here. And now we quickly switch the potential to this. And now the solution should be symmetric. So our wave packet, our particle distribution for symmetry, has to first accelerate up here the potential, then it has to decelerate down here. Yeah, so indeed it's very strange. If you think about stochastic perspective, this change of sign is very strange, but if you think it really makes sense. Okay, so we get some similarities, but there is if you have these, rotations on exponential drop or increase, you can get the Heisenberg principle also this way. For multiple particles, you can also it's very similar. So here is for non-interacting particles, here is for attracting particles, here is for repelling particles. So now we have to think about the tensor product, the joint distribution, but still we can do very similarly as in quantum mechanics. So finally, we can get these creation and annihilation operators, these combinatorics, very similar as quantum mechanics. So Bose-Hammatt model. So maybe let me summarize this physics part. So if instead of guessing the stochastic propagator, we do it right according to this maximal entropy principle, which is required to choose statistical physics model, then there is no longer disagreement with quantum predictions. So stochastic people do live in on world, but they can do better to get no longer in disagreement with quantum mechanics. The big question is, what are the consequences? So yes, also I think maybe molecular dynamics should think about it. They use standard diffusion, but I think these quantum corrections to molecular dynamics could be crucial. So I think there is a lot to do, but it's also very difficult to work. So it's too difficult for me to do it alone. So at the end, maybe let me to talk briefly about some different applications. For example, there is very nice article about many articles about using tractography, that they are able to make these maps of diffusion in brain, and maybe okay. And so the question is how to connect these local diffusion directions into tracts, and it's a very difficult problem because of noisy data and then like 200 algorithms. And they say that using this MERW-like approach, they were able to find these maximizing entropy tracks. Yeah, so literally, paths chosen to maximize information flow. So I think it's nice, but it's very difficult. Okay, so some different applications are some finding some the most important paths that they divide images into some superpixels, and they make some graphs between them, weighted graph, and use different random walks to find some important part, and they said that this MERW works the best. So finally, there are some centrality measures. So we have a graph. The question is, what is the importance of given vertex, and this eigenvector centrality is very similar to this MERW-like. For example, you could make this page rank on MERW, but it has much stronger localization properties, so I don't think it's good. So I think the standard random walk is better for humans as these drunken sailors, because indeed humans make local decisions. If a person sees a few possibilities, he uses probability distribution based on these local possibilities. So standard random walk is more appropriate here. And MERW is better if there is a very complicated behavior, but not made according to local decision. There is no this bias to choose JW. So I don't think MERW is good for. So this is example that not always MERW is a good choice. So I'll look at this again from that. Okay, so maybe this nice application to find the clustering on graphs. So basically they use often this mean first passage time that you start from vertex Mij is that you start from vertex I and perform random walk, and the question is what is the expected minimal time to get to J. So for standard random walk, you can see that this time is very narrow. But for MERW, you can see is much wider. So it is better to say that some are closed, so they are in one cluster, but other are in different cluster. Yeah. So for clustering on graphs, it seems nicer because it's much better distinguishes different vertices. There are many articles in this direction. And finally, the last application, computer science. So there is this link prediction problem. So if you have a graph of friends and you like to on Facebook to suggest a new friend, the question is how to do it. So there is basic SimRank. And that the question is what is the similarity between two vertices? And the original SimRank, so is that it has this kind of definition which looks nonsense, but it turns out it's quickly convergence. That you say that the similarity is the average similarity over neighbors. Yeah, so it sounds nonsense, but if you iterate it a few times, it quickly converges. And it turns out that there is equivalent formula to this that there is this expected F meeting distance that you take two walkers from positions A and B and ask what is the probability that they meet. And for this meet time, you use this function, which key is C to Z. If you do it, you get this similar formula. You get the same. So what they say, the question is, what is this random walk these walkers use? So this is for the standard random walk, but you can change to maximal entropy random walk, getting this formula, which is slightly different, uses these eigenvectors. So now it kind of works on the paths of possibilities, and they say that every time it works better. Yeah, so instead of thinking about single steps, they think about the space of entire paths, and it better recreates the behavior. So because yeah, so maybe let me use the final slide because it's more than 1 hour. So okay, so in many situations, so the question is, should it is in given situation, um, does the worker think about single steps, or maybe there is some, let's say, some chains of reason results, and we should think about the entire paths or instead of steps. So if we should think about steps, we should use standard random walk. If you think about paths, then we should use later maximal entropy random walk. So there are many. So it is, for example, this scale free. So DW has this scale as single step. MERV is limit for the infinite steps. Um, so yeah. There is a difference. So there are like 250 articles applying it for various ways. So thank you. Maybe let me finish and we can switch to discussion.
Okay, great. Thank you. Thanks, Jarek. Great talk. I can see one question from Ron, but actually it was already earlier. But let's read it. Maybe I'm not sure if have you maybe answered this question from the
Uh,
chat. The question is this similar to a spin or spin glass lattice, or is it the same thing? But it was already asked several slides
so
ago. So
So it's close to Isaac model, yeah. So generally we have maybe let's find slide for Isaac model. Okay, so generally yes, I think it's similar, but
So
yeah.
yeah, it was the slide with you had a
Oh yes, this one.
2D grid, and you're talking about magnetic poles and
yeah.
the rules for what the magnetism can be. It kind of reminded me of something I've
Yeah,
seen that has
so it
been
is very
labeled spin
similar.
or spin glass lattice.
Yeah, so Isaac model is ensemble of paths can be uniform in space. While here we focus on the ensemble of paths in time, also in quantum mechanics. Yeah, so but generally it's very similar. I can also with Isaac model I can get Bell variation, but in space instead of time. So mathematically it's very similar. Yeah, so that if we don't know what paths it was chosen both in space or in time, you should use uniform or Boltzmann distribution.
Thanks.
So
Yeah, I saw the reference to the icing model. I think it answered my question, but thank you.
thank you.
Mm-hmm. All right. Thank you. Do we have more questions to Jarek?
I have a question. How long do you think it would take to map a lot of those use cases in terms of the stochastic model and the model you're discussing, these open problems? There's quite a big range. I like how you put that, where we put it in the context of human capabilities. We look at more of a localized view of the world, and those models of diffusion work better for that. But mapping that out, what would you estimate that would take to map out, let's say, 30, 40 different variations of this, of which model works better for which application?
So generally people usually use it for some computer science physics applications, but just as to model physics, there are not many people. So I usually did most alone, but yeah. I need a collaboration. If somebody would like to, I gladly collaborate, but. I don't think I don't, yes I try to do it, but people from diffusion are focused on diffusion and they don't want to change. So it's, from quantum mechanics they want to do assume and then do Wick rotation. So that's very difficult to change people the way of thinking. You have two worlds and they don't talk to each other. Then they have on walls and don't do the same circles. So I don't know. I don't know how to change this society of people doing the same for decades, and they don't want to look at anything new and try change anything. That's a social problem, I think. And I think it's important. Yes, the question is especially for molecular dynamics. They use standard diffusion, but I think we should be very careful here. Yes, like they start observing tunneling for protons. This is standard now, so we should use quantum mechanics, but we could also use diffusion with quantum corrections. What can be done with these approaches? But it's difficult. So I'm looking for collaboration. But so if you know somebody, I will discuss.
The scope of this sounds pretty large, and you would need a multidisciplinary team to keep the neutrality of the thought process there and the bias out of it. And it seems like this could be a whole, applied research study in and of itself, just that.
Yeah, I completely agree, but I'm alone, so yes, I have 10 different projects also. Yes, so. I don't know how to move it forward. Yeah, so there is like 250 articles. So yes, if you can, but they go in different directions.
Great. Thanks, Eric. Do we have more questions? Helen, can you maybe check if there are some questions on YouTube?
So far, I don't see any question on YouTube. But anyone can unmute to ask questions.
Yes, yeah, you can also raise your hand and unmute.
So when I see graphs and references to the Ising model, have you explored some quantum solutions to solving things like QUBO or QAOA may or may not be a possibility?
So I think it's related for classical. This is a new approach that I think is slightly better than just Monte Carlo. So with MERW you can find analytically the probability distribution over these slices, and to find the probability distribution. So it's much faster than from Monte Carlo. But I wasn't, so I just put this arXiv and I wasn't able to find any collaboration. So yes, I gave up it.
Okay, thanks.
All right. Do we have more questions? If not, then I think we can finish for today. Helen, what do you think?
Yeah, sure. If you
Yeah.
have more questions, you can follow up
Yeah.
with Dr.
Okay.
Duda.
I did have one question, if I could.
Yes, please, Terry.
Sorry, I thought my space bar was working, but it wasn't. It says that my audio was working, but it didn't register. Jarek, on page 18, you have a line that's makes an interesting comment. Let me see if I can find it here. Discrete stationary Schrödinger equation, non-local depends on the entire graph. I just wondering if you could comment a little bit more about that non-local depending on the entire graph, because that's an interesting statement in terms of dependence, and I was intrigued by that. If you could just talk a little bit about that.
Sure. So maybe this one, yeah. So no, yes. So
Yes.
generally, yeah. So if you want standard random walk, then you just say you just think about this all the local situations. You just see what how many options you have, and you use probability one over the number probability. But for MERW, you need to find this eigenvector. You solve this equation, which is practically the Schrödinger equation, and solving this eigenequation requires knowledge of entire graph. Yeah, so it's no longer local information. You need the entire graph, the situation to get the stationary probability distribution. Yeah, so this is, but you have to remember that this is only statistical physics. This is model used by us, not by Walker. Walker just performs some very complicated behavior, and this is our model to find the most likely stationary probability distribution, for example.
Does the non-local effect, is that one of the criteria that you would use for finding the best applications of this method?
So non-local, I think, is the disadvantage, but generally this is how physics work. That if you want to find a probability of finding a Walker somewhere, you need to know the entire space he works on. If he uses a complicated dynamics, yeah. So non-local that you literally consider ensemble of all the paths that this Walker could consider. So for this purpose, you need to know the entire space he works on.
Yeah, I think I was thinking of the quantum case. Certainly non-locality would be a factor in some of the quantum situations.
Yeah, so the formulas are exactly as in quantum mechanics. So you get the same formulas for Schrödinger equation, but with more classical interpretation, you can say. Yeah, so you have a Walker which has some complicated behavior that you don't know what this Walker does. So you use the maximal entropy principle to find the safest stationary distribution, and to do it, you need to know the space this Walker uses. Yes.
Okay, thank you.
Okay. Do we have more questions to Jarek? Okay. Helen, I think we can finish for today. So I would like to thank everyone for coming. Jarek, thanks for the great talk, and thanks to everyone for interesting questions and discussion as well. And we hope to see you next time, next week. Jarek has just shared a link.
Yes.
Good. Thank
Yes.
you once again.
Sure. Thanks.
Thank you, Jarek.
Thank you.